Welcome to Data Science 1, Probability, Conditional Expectation. All right, so just give us a rundown of what we're going to have to think about here. Marginal distributions, conditional probability, and expectation rules. So here's the quick rundown of what a joint cumulative distribution function is, a joint probability density function, and the marginal probability density functions. The continuous one, the discrete ones are very similar, and you've seen them before in a previous video. This is just reminding you of the ideas. So let's look at marginal expectation before we jump into conditional expectation. And the reason we want to look at this is really simple. And basically, here's the idea is if we take the expected value of x, well, remember, we have a joint density here. We don't have necessarily the marginal, but we could get the marginal. But if we take the expected value of it, and then we put x, fxy, xy, dy dx, doesn't really matter. Well, yeah, here it does matter which order. And then we can pull this x out of this function because we can stare at this piece here and realize what I have in parentheses here is just the marginal distribution for x. So the expected value of x, if I use the full joint density, is going to be the same as if I just use the marginal density. And this is how you can calculate these rather easily, and this works for y as well. So if you know how to get it from the marginal, you'll be the same as if you got it from the joint. So it's kind of nice. Okay, so and we already know how to do this. All right, so the conditional distribution, if you remember it was the joint divided by the marginal, provided that the marginal is greater than 0. All right, so this is our setup here, and what we want to do is have conditional, our conditional probability gives us our expectation here. So we have expected value of y given x, and it's y times the conditional distribution, and notice x is out on the end, and we're integrating over y. Here we're summing over y times the distribution or the probabilities, and it works the same way for the other ones. Now, these are not interchangeable, by the way, so they are very, very different, and you'll see that these are really different once you start looking at the answers that come out of these. All right, so let's go back to our joint distribution that we've been considering. It's joint distribution. It's discrete. Let's start with expected value of x when y equals 0. Well, we're just going to be interested in this particular row here. So if you went back and you looked at that particular row, notice that this number is not the same as this number because I'm using the conditional distribution. So here I'm using the conditional distribution when y is equal to 0. I find the expected value and it comes up to 2.312. All right. So now we could go and do this again with the probability where y is equal to 1. So I've taken the original distribution. Now we're looking at this particular row, and we've turned it into a conditional distribution. And you can see when I take the expected value of it, I get, I get 2.194. So this is the distribution when y is equal to 1. The expected value of x when y equals 1 is 2.194. So it depends on the value of x, gives you whether or not you get what answer you get out of this. With regular expectation, we're used to getting one number. Well, here we don't get one number. We get a bunch of numbers depending on what the value of y is. And you'll see this come out even a little bit stronger in our next example. All right, so back to our continuous case example. Here's our density that we've been playing with, our joint density. I didn't work out the details. I left it for you to come up with the marginals, but here they are. So if I'm interested in the conditional distribution, which I think we did in the previous video as well, f of x, y, you just put one over the other, and bingo, this is what you end up with. And what we're interested in is the expected value of y given x. So here's what we're interested in. How do we do this? Well, we plug in our formula here, which means we plug in y times our density. And as we go along here, well, this all here with the x is just a constant with respect to y, so it can all be pulled out, which makes it easier. And then you can see I've got a whole bunch of steps here where we distribute it through, and then we do the integral from 0 to 2, and then we plug in 2 and 0, but 0 kills everything. So we end up with this distribution here, 6x squared plus 12x over 6x squared plus 8x. And if you reduced it down, you end up with 3x squared plus 6x over 3x squared plus 4x. And that's when x is between 0 and 2. And notice we didn't get a number out. We got a function of x out. Okay, and this is what usually throws people for a loop. Okay, I don't know what the expected value of y is until you tell me an x. When you tell me an x, I'll plug that in. And that sounds very familiar. Doesn't this sound like regression, right? You get a regression equation. They give you an x, and you can predict what y would be. Isn't that exactly what this is? Because what's the expected value of y? It's the mean of y given x. Give me an x, I'll tell you what the mean of y is. That sounds like a regression equation, and I would call this a theoretical regression equation. Okay, because if you've noticed here, there's no experiment involved. We haven't actually collected any data yet. We're just talking about things in the abstract or theoretical sense. So, there's this relationship that happens here as well as happens in the real world when we deal with real data. So keep that in mind as we go along here, because that becomes really important. All right, so marginal expectations are just the regular expected values, nothing exciting there. Conditional expectations are a bit odd in that they give you a function on the conditioning variable, which is not what you were expecting probably. You were thinking, oh, I'm just going to get a number like any other number. Here you end up with a function. This property can be viewed as a good thing because it tells us the mean for y for a given value of x, which is just like regression. All right, so in the next video, we are going to work through an example where we actually apply all of this with covariance and see what pops out. And then after that, we'll do the bivariate normal, and we'll see you there.